Hi everyone, welcome back to our channel. I hope you and your family members are doing good because that is the most important thing, and for rest we are here to talk. So we were following our pattern wise DSA sheet, and the pattern is serialization or construction, where we have to construct the binary tree or serialize it. So let's do the very first question, which is invert binary tree. So let's read the problem statement. It says we will be given the root of the binary tree and our task is to invert the tree. Invert means after construction of the tree, it should look like the mirror image of the original tree. Okay, so as you can see the example number 1, 4 will be at its place, but 2 was earlier 4's left child and 7 was right child. But after the invert, because now we have to create the mirror image, so right should come towards left side and left should go towards right side. That's what we are visualizing, right? So is it okay by just converting the parents left and right child? Because if we'll convert, then if you see, suppose 2 comes the right side, then after that 2 also has 1 and 3 as children, and it also needs to convert now, because when it becomes a mirror image, 1 is currently 2's left child, but after the conversion 1 should become the right child. So we have to repeat this left and right conversion for each and every node's left and right child. So let's read the constraint. It says the number of nodes can be 0 also, means we have to write the base case. What if the root is null? Okay, basically in DFS call, so for sure we have to write the base case, because recursively we call the same function and for sure at one time the root will become null, correct? But in DFS, if the root number of nodes can be 0, then for sure we have to write the base case, or else we don't need to. Why? Because if any one node is there, we prefer to store it in queue data structure. Remember, we already discussed how to do level order traversal using breadth first search approach. You can definitely check out the video if not yet. So hence no need to write the base case in the BFS if node is more than 0. Okay, and regarding the values, we know that integer can hold up to values up to 10 power 9 and it is only 10 power 2, so it's totally fine. So basically here is the tree we have, right? So we have to convert this tree into this, and we saw key 2 is the left child. After conversion 2 should become the right child. 7 is the right child. After conversion 7 should become the left child. Okay, so is it don't you think it's very simple ki if we have root, then it's something like ki we have to put right side in the left side and left side in the right side? We just have to swap it, right? Means not values, means suppose we are at root, means I can write DFS root. Okay, we are at parent. First, we all know ki we have to check if it is null or not. That's how we write. I'm not here directly writing the code. I'm trying to make you understand ki how, after seeing the problem statement, how to think for the to write the code. And also don't try to write the whole code in one go. Whatever you are able to understand, just write it down. Later on, if you feel you need to swap or rearrange the coding lines or create some variable or line of code, then you can later do it. Okay, that we will get to know when we will dry run our code. Okay, so first we have to write the base case ki if our root is null, then and there what should we return? See, here we are, here it is not null. Okay, we don't know suppose ki what to return. It's okay, go towards the left side and then right side, because that's what we do in DFS, right? We go in deep. So first we'll go to 2, okay, then again left side 1, then again, okay. So what do you think? What are we waiting for? Are we waiting for some number, or we were just looking to swap these 2 nodes? Just swap. We were not expecting anything from our children to give to parents, right? So you can simply return as it is. Okay, now here we are, it is not null. Now what is our task? Our task is this and this. Before going to left side and right side, we have access to left node and right node, right? Because we are at root. So we have root dot left and root dot right. So our task is to swap both of these. Using the temp variable. What we'll do, we have to swap. So suppose we want to put root dot right into root dot left. So before putting the value at root dot left position, we have to store it somewhere, and that we will store in node type temp variable. What will store? Root dot left. Very simple, like how we swap 2 numbers. That's how we are doing. Now at root dot left, which is the position of the node, we will change and replace it with root dot right. Now after these two lines, you know how our tree will look like? We will have 4, we will have 7, 6, 9, similarly 7, 6, 9. Why? Because we detached the left part and we saved it in temp variable. So temp variable has the access for this, okay? And now when at left place we copied right, so now we have duplicate right part, correct? Now what is our task? At right we have to update this with what we have stored in temp, which was earlier root dot left. So now what is our task? Root dot right, put what we have stored in temp, and that's it. So now what will happen? This will get replaced with this, correct? Done? Yes. But this though has been swapped, okay? 7 and 2, yes, correct. 4, 4, 7, 7, 2, 2, correct? At its correct position. But do you think it should be 6, 9 only, or it should be 9, 6? Because it is a mirror image. For every level it should become left into right side and right into left side, right? So don't you think we should repeat the same process for this child also and for this child also? So now from root, our task is to go on the left side. So now from root, if we'll go on the left side, so this will become root. And now again we have to swap their children's. Did you understood? And similarly we have to do for 2 also, which is root's right side. So basically we will call the same function root dot left and similarly for root dot right. And that's it. Okay. Okay. So this, like, we'll go here at 7. It is left side and right side. Again we'll put this in temp and this will update with right. 9, 9. So this will get updated with temp where we stored 6. So now this will become 9 and 6. Similarly, we'll go in DFS root dot right side. Here also we'll swap 3 and 1. Now done. Now once done, what do you think? At the end, what should be returned to the main function? Because the question was expecting to swap and return the root, correct? So can I write return root? Because when it will get swapped, when this will get swapped, 7 will get returned. Now this will get swapped, 2 will get returned. But we are not saving anywhere. Here see, we called left and right, but we are not saving anywhere. So this function will be returning 7. This function will be returning 2. But as we are not saving, so it is of no use. But why we are returning root then? Because for this at the last, because the question has called this DFS function and it is expecting the root to be returned after the swap. So hence after these 2 lines, we have to return root. Although we are not saving here, but from wherever, like the lead code or wherever at whatever compiler you are writing, from wherever you have, like this function has been called now, you are returning root to that function and for sure there they would be saving it or returning it as an answer. Okay. So this is via DFS. Now what is the time complexity? See, we traverse to every node. We traverse on the root and then we swap these 2. Then again we traverse on this, then swap their children. Then again we traverse to this. We don't have any children, but we traverse till 1, right? Similarly, we have traversed to each and every node. And if n is the number of nodes, here we saw the constraint, remember? That was 100 at max. So time complexity will be big O of n, which is 100. Very fast because it is very small. Constraint is very small. Talking about the space complexity, it will be O of h. Obviously, if you are following our playlist, you know what is h. H is nothing but height of the binary tree, which is O of log n, big O of log n, right? So space complexity will be this because in the recursive stack call, we are saving the calls, but at one level, only for one node we are calling. So hence, number of levels, which is height, which is log n. Okay, so this was the DFS code. Now let's write this in editor and then we'll see how to do with BFS. Remember, although DFS is the most preferred one, but still if you want to know how to do in BFS, we'll do that. But first, let's try to code it in the editor. So here is the editor we have. Now we have to write, first we'll write the base case, ki what if our root is null, okay? Ki if our root is null, return as it is. Very good. Now our task is to swap. So we have to make tree node type temp variable and here we have to store root dot left Okay, now in root dot left we have to write root dot right. Now in root dot right we have to put whatever we have stored in temp. Now our task is to call this same tree invert binary tree, right? Invert tree is the name of that. So we will call for root dot left. Similarly, we'll call for root dot right, and that's it. And at the end, we'll return root. That's it. Now let's try to run the code. Are we okay? We have to return null here. We have to return something, right? Why we have to return null? Because suppose initially only the root is null. Okay, then the return type is tree node, right? So you have to return null. Okay, now let's try to submit this, and that's it. So this was a DFS code in Java. Here is the DFS code in C++, similar approach, and here is the DFS code in Python, similar approach. Okay, so I hope you understood. Now the task is ki how to do in breadth first, like using breadth first search approach. So what do you think? Like in BFS, what we are going to do? Definitely we have to save all the nodes as per the levels. So in the queue data structure, first we will have 4, correct? Now what you want to do with 4? We don't want to do anything with 4, but we want to swap 4's left and right children. So very simple, when we'll pop this node, now for this node we have left and right, so there we will swap like how we did in the DFS approach. Now in the next call we will save left and right children in the queue 2 and 7, so that later on we'll pop this and then swap their children. So I'm not going to explain how to do BFS approach because I have already taught in our previous video. I will definitely recommend you all to go and check out there. I'll directly show you the code ki how we will store the nodes as per the levels in the queue data structure. Then we'll pop one by one, and once we have popped the node, now we have the access for left and right child. Now we'll swap the nodes similarly as how we did in the DFS approach. So here is the code. First, because the root can be 0 also, number of nodes can be 0. So if root is null, return null. Then we'll make a queue data structure. There we'll insert the very first root. Now until the queue becomes empty, we will start popping the nodes, and using that extra like third variable, we will swap all of these. Now task for the root is done. Now what about the next one? Because in DFS, so we are going with root dot left and root dot right call with the recursive approach. But here for the next level, we have to store their childrens in the queue data structure, right? So hence, if our nodes, which is current, left child is not null, then in the queue we have to insert. Similarly for right child, because that's how we do the level order traversal using BFS approach. I hope you know that. And at the end, we just have to return the root. This code is also very simple, and the time complexity will be O of n, because here also we are actually iterating for all the nodes only, and we are not repeating for any node again. So hence the time complexity will be big O of n, but the space complexity will be, here it will be width instead of height. Width means, see, height means from every level 1 1. So height is nothing but logarithmic of n. But width is, in the first case you will be saving just one node from the first level. In the second time you will be saving 2 nodes from the second level, and the last 4 nodes in the third level, right? So the space complexity will be maximum width. So this is our code. Let's try to run this. Definitely this is also the optimized approach only, but we prefer going through DFS approach whenever we have to invert the trees. Okay, so this is your Java code for BFS approach. Here is the C++ code for the BFS approach, and here is the Python code for the BFS approach if you're from Python background. So I hope you understood both DFS and BFS approach. If yes, and if you are able to do on your own instead of just watching the video, then you are definitely eligible to go in the sheet and mark the very first question as done. And that's it. I'll attach the sheet link and my social media links in the description. If you understood and if you submitted, then please make sure to comment down that yes, you understood, and please hit the like button if you really like the way of teaching. And that's it. Let's meet in another video with some more interesting questions, topics and patterns, and then keep learning. Take care of yourself and your family.